Hey there, welcome to For Science Salah Lotfy channel. Today I'm thrilled to dive into a revolutionary topic in material science with a twist of space magic. Picture this, our spacecraft braving the harsh vacuum of space, dodging high-speed micrometeoroids, and enduring extreme thermal swings. To survive, we need materials that are strong, lightweight, and super durable. Enter Shape Memory Polymers. These are no ordinary materials. They can return to their original shape when exposed to stimuli like heat or light. Imagine the possibilities for satellite deployment mechanisms. Lightweight, flexible, and incredibly resilient. In recent studies, researchers have taken this a step further by investigating epoxy nanocomposites reinforced with multi-walled carbon nanotubes, or MWCNTs. These nanocomposites were meticulously prepared and enhanced with special additives. The goal? Improve properties like surface tension and resilience under high radiation doses. The results are mind-blowing. Specific additives help distribute the carbon nanotubes more evenly, boosting stability and mechanical strength. This means our satellites can now handle even harsher conditions with ease. This groundbreaking research highlights the potential of these advanced materials in space missions. Their adaptability and resilience make them game changers for satellite technology, increasing durability and performance in the most extreme environments. So let's dive deeper into this incredible innovation that's propelling us toward the future of space exploration and satellite tech. Stay curious and keep exploring. Hey everyone, welcome back to For Science Salah Lotfy channel. If you're fascinated by space research, you're in for a treat today. We're diving into an exciting new research paper that's making waves in satellite technology. The study is titled Influence of Gamma Irradiation on Shape Memory Polymer Nanocomposite for Satellite Deployment Mechanism. So, what's this all about? Well, the paper explores how gamma radiation can affect the properties of nanocomposites, which are crucial for deploying satellites in space. This groundbreaking research was a collaborative effort from some of Egypt's top institutions. Leading the charge is Professor Dr. Emad Mousa from Cairo University's Physics Department. His work focuses on how materials behave under extreme conditions, a must-know for space tech development. Next up, we've got Professor Dr. Eman Taha from the Egyptian Petroleum Research Institute. She's an expert in applying these materials in harsh environments, ensuring they perform reliably out there in the vastness of space. And we can't forget Professor Dr. Salah Lotfy from the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority. His deep dive into polymer chemistry and radiation applications was key in optimizing these nanocomposites to withstand gamma irradiation. Last but not least, Professor Dr. Ahmad Anwar from Pharos University in Alexandria contributed his mechanical engineering expertise. He analyzed the deployment mechanisms and checked the structural integrity of the nanocomposites. Published in Scientific Reports by Springer Nature on October 13, 2024, this study was first received on July 18 and accepted on September 19. Thanks to the Springer Nature Shared IT initiative, it's widely accessible, spreading these valuable insights far and wide. This research lays the groundwork for creating more reliable and efficient satellite deployment mechanisms. By using gamma-irradiated shape memory polymers, we could revolutionize how we design space technologies, making future missions safer and more effective. Stay tuned as we delve deeper into this study and uncover how each team member's expertise has driven these advancements. It's an exciting time for space science and material engineering. Thanks for watching, and don't forget to like, share, and subscribe for more fascinating updates from the world of science.
Space is a dangerous place. It's super cold, there's no air, and radiation blasts everything. The environment is incredibly harsh, and any equipment sent up there needs to be able to withstand these extreme conditions. From the freezing temperatures to the intense radiation, space is not a friendly place for technology. Satellites need tough materials to survive. Engineers and scientists work tirelessly to develop and test these materials. They spend countless hours in labs, ensuring that every component can handle the rigors of space. The materials used must be resilient, durable, and capable of withstanding the harshest conditions. Ordinary stuff breaks down quickly in space. That's a big problem. When materials degrade, satellites can fail, leading to loss of communication, navigation, and other critical services. The stakes are high, and the need for reliable materials is paramount. Engineers must constantly innovate to find solutions that can endure the test of time in space. We need our satellites to last a long time. Longevity is key to ensuring that satellites can continue to provide essential services without frequent replacements. Maintenance and repairs in space are incredibly challenging and costly, so the goal is to create satellites that can operate efficiently for many years. Shape Memory Polymers, or SMPs, might be the answer. These innovative materials have the unique ability to return to their original shape after being deformed. Scientists are exploring their potential to revolutionize satellite technology. SMPs could be the key to creating more resilient and adaptable satellites. They can change shape with temperature. This property allows them to adapt to different conditions in space. For example, SMPs can be programmed to unfold or change shape when exposed to specific temperatures, making them incredibly versatile for various applications. Imagine a satellite unfolding itself in space. This capability can significantly enhance the functionality and efficiency of satellites. By using SMPs, satellites can be designed to deploy components only when needed, reducing the risk of damage during launch and increasing their overall lifespan. These SMPs are made even tougher with tiny particles called nanocomposites. By incorporating nanoparticles, scientists can enhance the strength, durability, and thermal stability of SMPs. This combination creates materials that are not only adaptable but also incredibly robust. We're talking about materials that are strong and light. The lightweight nature of these advanced materials is crucial for space applications where every gram counts. By reducing the weight of satellites, we can lower launch costs and increase the payload capacity, making space missions more efficient and cost-effective. Epoxy is a strong glue. MWCNTs are tiny tubes of carbon, super strong and light. Mix them together and you get a super material. These nanocomposites are great for space. They can handle extreme temperatures and radiation, plus they are very lightweight. This is important because launching things into space is expensive. Lighter materials mean less fuel and lower costs. Epoxy MWCNT nanocomposites are like giving satellites a suit of armor. They'll be ready for whatever space throws at them. Space is full of gamma rays. These rays are powerful and can damage satellites. We need to test how our materials hold up. Scientists use gamma irradiation to simulate space radiation. They blast the materials with gamma rays in a controlled environment. This helps us understand how the materials change. We can then improve them to be more resistant to radiation. It's like giving our satellites a crash course on surviving space. We make sure they're ready for the real deal. Making these nanocomposites is tricky. The MWCNTs like to clump together. That weakens the material. Surface tension is like a force that makes liquids want to stay together. Think about how water forms droplets. Surfactants are like soap. They reduce surface tension and help mix things up. We use them to disperse the MWCNTs evenly. Getting the right mix is important for strong and durable materials. It's like making sure all the ingredients are evenly distributed in a cake. Section 5. Feeling the heat, thermal, and viscoelastic properties. In this section, we delve into the fascinating world of how materials behave under varying thermal conditions and their viscoelastic properties. Understanding these properties is crucial for the development of materials that can withstand the harsh environments of space. Spacecraft experience extreme temperature swings. These swings can range from the intense heat when exposed to direct sunlight to the frigid cold when in the shadow of a planet or in deep space. The materials used in spacecraft must be able to endure these drastic changes without degrading. From the heat of the sun to the cold of deep space, the thermal environment is incredibly challenging. The sun-facing side of a spacecraft can reach temperatures of up to 250 degrees Celsius, while the side facing away from the sun can plummet to minus 150 degrees Celsius. This extreme thermal cycling can cause materials to expand and contract, potentially leading to structural failures if not properly managed. We use tests like TGA and DMA to see how materials react to temperature changes. Thermogravimetric analysis, TGA, and dynamic mechanical analysis, DMA, are essential tools in our arsenal. These tests help us understand the thermal stability and mechanical properties of materials under different temperature conditions. TGA measures weight loss as things heat up. By heating a material and measuring its weight loss, we can determine its thermal stability and decomposition temperatures. This information is vital for ensuring that materials will not degrade or lose their integrity in the extreme temperatures of space. DMA tests how springy a material is at different temperatures. It measures the material's stiffness and damping properties, providing insights into how it will perform under mechanical stress at various temperatures. This is particularly important for materials that will experience both thermal and mechanical loads in space. This helps us understand how it will behave in space. By analyzing the data from TGA and DMA tests, we can predict how materials will perform in the harsh conditions of space. This allows us to select the best materials for spacecraft construction, ensuring their reliability and longevity. Epoxy MWCNT nanocomposites perform well in these tests. These advanced materials combine the strength and thermal stability of epoxy with the exceptional mechanical properties of multi-walled carbon nanotubes, MWCNTs. This combination results in a material that is both lightweight and incredibly strong. They stay strong even in extreme temperatures. The nanocomposites maintain their structural integrity and mechanical properties even when subjected to the extreme thermal cycling of space. This makes them ideal for use in spacecraft components that must endure harsh thermal environments. That's what we need for space. The ability to withstand extreme temperatures and mechanical stresses is crucial for the success of any space mission. By using materials like epoxy MWCNT nanocomposites, we can ensure that our spacecraft are built to last and can safely carry out their missions in the unforgiving environment of space. Section 6. Shape-shifting satellites, the magic of shape memory. In the vast expanse of space, satellites play a crucial role in communication, navigation, and scientific research. But have you ever wondered how these marvels of technology are designed to withstand the harsh conditions of space? Enter the world of shape memory polymers, or SMPs, a groundbreaking innovation that is revolutionizing satellite technology. Shape memory is the superpower of SMPs. These materials have the unique ability to remember a predetermined shape and return to it when exposed to a specific stimulus, such as heat. This remarkable property is what makes SMPs so valuable in the field of aerospace engineering. They can be trained to remember a shape and return to it when heated. Imagine a coiled spring that can be stretched out and then, with a bit of heat, snaps back to its original form. This is the magic of shape memory in action, and it's being harnessed to create more efficient and reliable satellite components. Imagine a satellite packed up tight for launch. Space is a premium and every inch counts. By using SMPs, engineers can design satellite components that can be compactly stored during launch, saving valuable space and reducing the overall weight of the satellite. Once in space, it uses the sun's heat to unfold itself. No bulky mechanisms needed. This self-deploying feature is not only ingenious, but also incredibly practical. The sun's heat acts as a natural trigger, causing the SMP components to expand and take their intended shape, ready to perform their functions. This can make satellites lighter, cheaper, and more efficient. By eliminating the need for complex mechanical systems, SMPs reduce the overall weight and cost of satellite construction. This efficiency translates to more affordable space missions and the ability to launch more satellites within the same budget. Plus, it opens up new possibilities for space exploration. With SMPs, the design possibilities are endless. Engineers can create innovative satellite structures that were previously unimaginable, paving the way for new missions and discoveries in the final frontier. Epoxy MWCNT nanocomposites add strength and durability to this superpower. By combining SMPs with advanced materials like multi-walled carbon nanotubes, MWCNTs, scientists are enhancing the performance and resilience of these shape-shifting components. This synergy results in satellite parts that are not only flexible, but also incredibly strong and durable. It's a winning combination for space technology. The integration of SMPs and nanocomposites is setting new standards in the aerospace industry, leading to more successful satellite launches and groundbreaking innovations. The future of space technology is brighter than ever, thanks to the magic of shape memory. Section 7. A new era for space exploration. The future is bright. These new materials could change the game for space exploration. Imagine lighter, more durable spacecraft exploring the solar system. We could build bigger telescopes, send probes to distant planets, and maybe even build structures in space. The possibilities are endless with these innovative materials. It's an exciting time to be studying space technology. Section 8. The importance of continued research. We've made great progress, but there's still much to learn. We need to keep researching and improving these materials. We need to find even better ways to make them, test them in extreme conditions, and explore new applications. Continued research will ensure that we can push the boundaries of space exploration. The future of space travel depends on it. Section 9. Conclusion. Tiny materials, giant leaps. Epoxy MWCNT nanocomposites are revolutionizing satellite technology. They are strong, lightweight, and resistant to harsh space conditions. Combined with the magic of shape memory, these materials have the potential to transform space exploration. It's amazing how such tiny materials can lead to giant leaps in technology. The future of space exploration is bright.
Imagine a material, strong and versatile, used in everything from airplanes to wind turbines. This is the promise of epoxy composites, known for their exceptional strength and lightweight nature. Our journey explores surfactants and gamma radiation, and their impact on epoxy composites reinforced with multi-walled carbon nanotubes, or MWCNTs. MWCNTs are tiny cylinders of carbon atoms, incredibly strong and light. Surfactants ensure a smooth and even distribution of nanotubes in epoxy. Gamma radiation can alter the molecular structure, enhancing strength and stability. Join me as we uncover the secrets behind stronger and more resilient epoxy composites. Picture a drop of water beating up on a waxed surface. This occurs due to surface tension, a force that causes liquids to minimize their surface area. In epoxy composites, surface tension affects how MWCNTs disperse within the epoxy matrix. High surface tension causes nanotubes to clump like oil and water. Surfactants lower surface tension. They help MWCNTs mix smoothly with epoxy. Imagine a spacecraft re-entering the Earth's atmosphere, enduring scorching temperatures. This intense heat resistance is a critical requirement for many materials, including our epoxy composites. To test their mettle, we subjected them to thermogravimetric analysis, a technique that measures weight loss as a function of temperature. This analysis revealed the thermal stability of our epoxy composites, providing valuable insights into their behavior under high temperatures. We observed that the addition of MWCNTs generally increased the thermal stability, a testament to their robust nature. However, the real surprise came when we introduced gamma radiation into the equation. Exposing the composites to varying doses of gamma radiation led to intriguing results. In some cases, the thermal stability further improved, suggesting that the radiation induced beneficial cross-linking within the epoxy matrix. This cross-linking acts like molecular bridges, strengthening the material and enhancing its resistance to heat. These findings highlight the potential of gamma radiation as a powerful tool for tailoring the properties of epoxy composites. Imagine pushing a boulder up a hill. The steeper the hill, the more energy you need to move it. Similarly, in the world of chemistry, activation energy represents the minimum energy required for a reaction to occur. In our case, we were interested in the activation energy for thermal decomposition, a measure of how easily the epoxy composite breaks down when heated. By analyzing the thermogravimetric data, we could calculate the activation energy for different composite samples. We found that the presence of MWCNTs generally increased the activation energy, indicating that more energy was required to initiate thermal decomposition. This finding further reinforces the role of MWCNTs in enhancing the thermal stability of the composite. Interestingly, the activation energy also varied depending on the gamma radiation dose. This suggests that the radiation altered the decomposition pathway, influencing the energy barrier that needs to be overcome for the material to break down. Understanding these subtle changes at the molecular level is crucial for optimizing the performance of epoxy composites in high-temperature applications. Imagine a bridge swaying gently in the wind, its structure responding to external forces. Similarly, all materials exhibit a certain degree of deformation when subjected to stress. Dynamic mechanical analysis, or DMA, allows us to study these viscoelastic properties, providing insights into how a material behaves under various conditions. We employ DMA to investigate the mechanical properties of our epoxy composites, focusing on how they responded to stress at different temperatures. The results were fascinating, revealing the profound influence of gamma radiation on the material's behavior. In some cases, the irradiated samples exhibited increased stiffness, indicating enhanced resistance to deformation. This increased stiffness can be attributed to the cross-linking induced by the gamma radiation. These molecular bridges act like tiny reinforcements within the epoxy matrix, making it more difficult for the material to deform under stress. However, it's crucial to note that the effect of radiation on mechanical properties is not always linear. Finding the optimal radiation dose is key to achieving the desired balance of strength and flexibility. Section 6. The future of epoxy composites, stronger and more resilient materials. Our exploration into the realm of surfactants and gamma radiation has unveiled their remarkable potential in enhancing epoxy composites. By carefully selecting the right surfactant, we can ensure a uniform dispersion of MWC&Ts, unlocking their full strengthening capabilities. Gamma radiation, on the other hand, offers a powerful tool for tailoring the thermal and mechanical properties of these composites. The increased thermal stability achieved through gamma radiation is particularly noteworthy. Imagine epoxy composites capable of withstanding even more extreme temperatures, opening up new possibilities in aerospace applications, engine components, and fire-resistant materials. This enhanced heat resistance paves the way for safer and more reliable structures, pushing the boundaries of material science. Furthermore, the ability to fine-tune the mechanical properties through radiation exposure is a game-changer. Imagine epoxy composites with tailor-made stiffness and flexibility, perfectly suited for specific applications. From lighter and stronger aircraft components to more durable wind turbine blades, the possibilities are endless. Section 7. Beyond the lab real-world applications of enhanced epoxy composites. The advancements in epoxy composite technology hold immense promise for a wide range of industries. Imagine lighter and more fuel-efficient aircraft soaring through the skies, their wings crafted from these enhanced materials. The automotive industry could also benefit significantly with stronger and lighter car bodies made possible by these advanced composites. Beyond transportation, the construction industry stands to gain from the increased strength and durability offered by these materials. Imagine bridges and buildings that are not only stronger, but also more resistant to environmental degradation, ensuring long-lasting infrastructure. The renewable energy sector could also benefit, with wind turbine blades made from these enhanced composites capable of withstanding harsher conditions and generating more power. The applications extend even further, encompassing sporting goods, electronics, and even biomedical devices. Imagine lighter and stronger tennis rackets, more durable smartphones, and even biocompatible implants made possible by these versatile materials. The future of epoxy composites is bright, promising a new era of innovation and technological advancements. Section 8. Ethical considerations, balancing innovation with environmental responsibility. As we venture further into the realm of advanced materials, it is crucial to acknowledge the ethical considerations that accompany such innovation. The production and disposal of epoxy composites, like any material, have environmental impacts that must be carefully assessed and mitigated. One important aspect is the development of sustainable manufacturing processes for these enhanced composites. This includes exploring the use of eco-friendly raw materials, reducing energy consumption during production, and minimizing waste generation. Additionally, research into the recyclability and biodegradability of these materials is crucial to ensure their responsible disposal at the end of their life cycle. Furthermore, it is essential to consider the potential health and safety aspects of working with gamma radiation. Strict safety protocols and regulations must be in place to protect workers and the environment from any potential risks associated with radiation exposure. By prioritizing both innovation and environmental responsibility, we can pave the way for a sustainable and ethical future for epoxy composite technology. Section 9. Conclusion: a new era for epoxy composites. Our journey into the world of surfactants and gamma radiation has illuminated a path towards stronger, more resilient, and versatile epoxy composites. By understanding the intricate interplay between these elements and the epoxy matrix, we can unlock a new era of material science. Imagine a world where these enhanced composites revolutionize industries, from aerospace to construction, enabling lighter, stronger, and more sustainable structures. The future holds exciting possibilities as we continue to explore the full potential of these materials. Further research into novel surfactants, optimized radiation doses, and innovative manufacturing techniques will undoubtedly lead to even more remarkable advancements. As we push the boundaries of material science, we must also remain mindful of our responsibility to the environment and future generations, ensuring that these innovations contribute to a more sustainable and equitable world.
Thank you for joining us on the For Science Salah Lotfy channel to explore this pioneering research on the development of advanced materials for satellite deployment. We extend our deepest gratitude, respect, and appreciation to the esteemed researchers whose contributions made this study possible. We start by honoring Professor Dr. Emad Mousa from the Physics Department at the Faculty of Science, Cairo University, Giza. His dedication to studying materials under extreme conditions has laid the groundwork for innovations in space technology. We also thank Professor Dr. Eman Taha from the Petroleum Applications Department at the Egyptian Petroleum Research Institute, Cairo. Her expertise in applying materials in challenging environments has been instrumental in this research. A special thanks to Professor Dr. Salah Lotfy from the Polymer Chemistry Department at the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority. His knowledge of polymer chemistry and radiation applications was vital in ensuring the nanocomposites could endure gamma irradiation. And finally, Professor Dr. Ahmad Anwar from the Mechanical Engineering Department at Pharos University in Alexandria. His engineering expertise contributed to analyzing the structural integrity of these innovative materials, a critical aspect of successful satellite deployment. We also thank you, our dedicated viewers, for supporting us on this journey of scientific discovery. Don't forget to subscribe to the For Science Salah Lotfy channel and follow us for more insights into groundbreaking research. Until next time, stay curious and stay inspired.